Great, so thanks everyone for coming. This is based on joint work with some really awesome collaborators with Ainesh Bakshi, Liu and Ewin Tang. So I'm a newcomer to quantum spin systems, but I've spent a lot of time thinking about classical spin systems. So in this talk, I'll tell you about some cool results about quantum spin systems, specifically about phase transitions and entanglement. But really what I want to emphasize the most are the metaphors with classical cases. Because I think there's a lot of opportunities to try and build what is this dictionary between what do we know classically and what can we hope to say from a quantum standpoint. So I'm going to try and introduce these things really from a classical perspective first. So let me start off with introducing some of the basics of statistical physics, because that's really the perspective that I want to take before I get to the quantum case. So statistical physics is, a remarkable feat of 19th century physics, where the basic guiding question is how do local interactions between different molecules or particles give rise to very complex macroscopic behavior? And these aren't, exotic things, they're very down-to-earth things. Like maybe the simplest example of these macroscopic phenomena that we want to understand are things like magnetism. So magnets are familiar to all of us. We've certainly all played with them when we were kids. Maybe we still play with them now, no judgment. But how does a magnet work? So in your material, you've got electrons, and they're each spinning. And they have a choice of how to orient their spin. They can orient it in a clockwise or counterclockwise direction. And of course, when the electron is spinning, it induces a local magnetic field. And the choice of how the spin is oriented affects the choice of how the local magnetic field is oriented as well. So what is magnetism, this macroscopic phenomenon that's familiar to all of us? All it is when we have a material where most of the spins line up in the same direction, so that you have a macroscopic magnetic field. And the way to think about these things is you can imagine in your material you might have electrons that are nearby each other, and you can imagine that they communicate with each other through some physical forces and mechanism. But when you have electrons that are very far away from each other in the material, how exactly do they all decide on which way if they don't directly communicate with each other? So that's what statistical physics is about, it's about this microscopic modeling of the interactions, say, between spins of electrons and macroscopic phenomena, things like magnetism that we'd like to understand. Even better, we'd like to probe how these macroscopic phenomena are controlled by things like the strength of the interaction, the temperature at which the materials are living. But to dive a bit more into the details, for things like ferromagnets, the basic principle is very simple, is that neighboring spins on the lattice, they prefer to point in the same direction. Now the physics that gives rise to that is a little bit complicated. It involves something called an exchange interaction. But for us, this is the starting point of what statistical physics is. What you do is you define a probabilistic model that describes a probability distribution over all configurations that these spins could be in. And that's a truly gigantic set, but you define this distribution in a compact way based on writing down some energy functional. And you study properties of this distribution as a way to understand these macroscopic phenomena. That's what statistical physics is about. So the standard example that you see the first time you talk about these things in classical spin systems is the Ising model. So there are a lot of terms here, and I'll go through and explain them. Probably many of you have seen them, but this will be a good opportunity to make sure that we're on the same page in terms of the notation. So first, I'm defining a distribution on plus minus 1 to the n. So I think about there as being n different electrons. And the corresponding variable, it's plus 1, that tells me that the magnetic field is oriented in one direction. And if it's minus 1, it's oriented in the opposite direction. So I'm defining a distribution on states of my system. Now, I would never hope to write down that distribution just in a table, because then I'm writing down 2 to the n probability values. And there's no interesting way to work with those objects. So instead, what you do is you define a distribution implicitly through defining a Hamiltonian. So this Hamiltonian h is going to be a function. It takes my configuration little x that lives in plus minus 1 to the n, and it spits out the energy of that configuration. And for an Ising model, all it is it's the sum of two terms. One of them is a quadratic interaction term, and the other term is linear in the x's. And the way to think about what each of these terms do is to think about them in isolation. So if I had no interactions, then I would end up defining a distribution that's a product distribution. So it's independent across all of the coordinates, but my corresponding external field HI would tell me, how much the external magnetic field favors one direction over the other. Right? So that's what this first term means. This is this linear term in my energy function. And then, of course, what's critically important for us are the interactions between spins. So that's captured by this interaction matrix J. That's an n by n matrix. And the way to think about it is that if you look in the ith row and the jth column, the value in the matrix tells you how much I and j prefer to point in the same or opposite directions. And you get things like ferromagneticity and anti-ferromagneticity based on some choice of whether these should be positive or negative signs. So now we have a Hamiltonian, given some configuration on the state space, it spits out an energy. And the remaining thing that we need to do in order to define a distribution is we set an inverse temperature beta. So if you think about beta, which is our inverse temperature, is going off to infinity, then what's going to happen is that this distribution is concentrated only on the minimizers of h of x, so the ground states. But now as beta becomes very small, the inverse temperature is becoming very small, so we're heating up our system, then we tend to favor distributions that have higher entropy, even though they might end up with a larger energy. And the entire thing, finally, we normalize it so that it really is a distribution, and that's the partition function. So this is what an Ising model is. There's a lot of beautiful mathematical questions that you can study about this that have very deep physical significances. And you can generalize it in a lot of natural ways, right? What happens, for example, if I want higher order interactions? It's not just pairs of spins that are interacting. Maybe I've got triples of spins, quadruples of spins. That really is just a minor change on this model where instead of having a degree 2 polynomial sitting upstairs for my Hamiltonian, I might have a higher degree, like a degree k polynomial, right? So any questions about this? Please stop me anytime if you guys have questions. All right. So, these are oftentimes called graphical models. And one of the reasons for that is because by looking at an associated graph to your Ising model, you can learn a lot of important properties about the distribution you're defining. So if I take my Ising model and I form a graph where I've got n nodes, each one represents a coordinate in my random variable, then I can create an edge set on this graph whenever there's a non-zero interaction. And by assumption, we're always going to assume that this interaction matrix J is symmetric. So we're really going to get undirected edges here. And the critical defining property in the classical case, the thing that we exploit all the time when we talk about sampling or learning algorithms, is what's called the Markov property. So the way that this works is that if you're given two spins, I want to figure out whether the spin at site I is pointing up or down. I want to figure out whether the spin at site J is pointing up or down. In general, they won't be independent, but they'll have a lot of nice conditional independence properties. So if you tell me some other spins in my lattice, then it might turn out that based on what you've told me, I and j are now independent, right? And so the critical point is that this Markov property, comes from the separators of the graph. So if you take your Ising model and you write down this graph based on which pairs of spins actually have a non-zero interaction, and you give me any pair of sites I and j, and you condition on another set of sites u, as long as they're a graph-theoretic separator, there's no path that starts at I, ends at j, and avoids u, you'll have the property that you are guaranteed that the distribution you've defined has this conditional independence property. So this is the part that makes a lot of sampling and learning possible, is really exploiting this property. And if we're trying to build this dictionary between what happens in classical spin systems, what happens in quantum spin systems, I should warn you about the things that are going to come later. When we talk about quantum spin systems, a lot of the things that we hold near and dear classically are just going to go completely out the window. So there are ways to talk about the Markov property. Unfortunately, it fails very badly exactly for entanglement. So, one of the really fun things about talking about classical spin systems is you can draw very pretty pictures, and there's a lot of beautiful, deep mathematics. It's led to Fields medals, a lot of interesting things have come out of it. And, one way to visualize what these models look like is to take a typical sample from an Ising model, let's say a ferromagnetic one, where neighboring spins prefer to be pointing in the same direction, and then to think about varying the temperature. And so what I've drawn here is, imagine that you have a white dot for a spin that's pointing in one direction. You've got a black dot for a spin that's pointing in another direction. Now, if I take a typical sample from the Ising model, at high enough temperature, this is what it looks like. It just looks like noise. It looks like a speckled pattern of, black and white squares. But, as you slowly decrease temperature, something very beautiful happens, which is you end up with almost all of the spins pointing in the same direction, right? And this is what's called a phase transition, is when you have a dramatic change in the macroscopic properties of your system, that are driven by these microscopic interactions. So people know lots of beautiful things like, in fact, these transitions happen very sharply. So there's in general a very critical temperature at which you change very quickly from this picture to this picture. And there's a lot of deep works on trying to understand where those phase transitions happens, what are the algorithmic implications for them, what kinds of structural properties you can prove about a typical sample from this distribution, right? So now we should start talking about quantum spin systems. So the same way classical spin systems were a way for us to describe what a system looks like at thermal equilibrium, well, now I want to understand what does a quantum system look like at thermal equilibrium. So usually, if I give this talk, which I've only given it a couple times, I don't know much quantum, but the audience knows even less quantum than I do, so I have to introduce quantum. Here we seem to be in the reverse situation. So let me tell you how I think about it, okay? And that's just for me. You guys already know all this stuff. But at least it'll give me an excuse to make sure that we've got the same notation in mind. So we all know what a density matrix is. So it's of an n qubit system. It's a 2 to the n by 2 to the n matrix. Of course, we require that it's positive semi-definite, and critically, it better be trace 1, right? And at least the way that I like to think about these is sort of as a non-commutative generalization of classical distributions. Like, what if I took a density matrix, it's 2 to the n by 2 to the n, it's positive semi-definite, it's trace 1. But I add this further restriction that not only does it satisfy those properties, but also it's diagonal. So in that case, if it's positive semi-definite, if it's diagonal, if its trace is 1, then I have no choice, but all of the values along the diagonal are all non-negative, and they better also sum to 1. So this is our distribution sitting right there. Remember, I told you for classical distributions, you never want to write them down explicitly, as a 2 to the n table of all of the probabilities of every configuration. But that's exactly what the density matrix would do in the special diagonal case, because they'd show up exactly as these diagonal entries, right? So now we also have to think about what it means to generalize this two-local Hamiltonian that only cares about pairs of interacting spins or triples of interacting spins. And the way we think about this is we think about terms HE that are going to compose our Hamiltonian, which we can build up in simple ways. Even though they're 2 to the n by 2 to the n matrices, we can describe them much more succinctly. Like, what if I told you a 4 by 4 matrix A, and then I tensor it with a bunch of copies of the identity? Well, then we should think about this like a term in the Hamiltonian that only cares about the first 2 qubits, because it's an identity on the rest of the system. And more generally, we can think about these k-local Hamiltonians as being ones where you tell me a 2 to the k by 2 to the k matrix. That tells me what is the interaction between the corresponding k tuple of qubits. But then you also tell me what its support is, so which k qubits it actually interacts on, and the rest of it is tensored with the identity, right? So I like to think of this obviously as a generalization of the types of local interactions that we use to describe what is the energy of our system in the classical setting. So now we're good because we can talk about what the quantum Gibbs state is. We've already seen it many times, but I'm going to think about the terms of the Hamiltonian as each of them being k-local, so they're the tensor product of k Paulis. So that already induces some normalization on the EAs. But then I'm going to allow you to add up these terms in the Hamiltonian with weights lambda A. But I'm going to impose some constraint that maybe the absolute value of the lambda A's is at most 1. Because really what I'll care about is how this inverse temperature beta affects properties of my quantum Gibbs state. And I'm just choosing some normalization so that we have some well-defined way to measure what this beta is. But the quantum Gibbs state is sort of the obvious thing. It was e to the minus beta h before, and that's what it is now. We take our 2 to the n by 2 to the n Hamiltonian, we multiply by this inverse temperature, and now we take the matrix exponential. So this is already a little bit different because before our Hamiltonian was a function that takes in the state of the system, but now it's this giant object that we can never hope to actually explicitly write down, right? And of course, by construction, this quantum Gibbs state I've written down here is a density matrix. It's definitely PSD and trace 1. And now I can get to at least one of the main questions that I'll be interested in for this talk, is the same way that we cared about how temperature affects macroscopic phenomena like magnetization that people have studied for a long time in statistical physics. What about how temperature affects the types of resources we care about in quantum spin systems? So how does it affect things like entanglement? All right, so last little bit of quantum background for me, not for you, is how are we thinking about entanglement? So measuring entanglement in a general density matrix is a bit challenging to define. But for our purposes, I'll just be concerned more with the crude question of what kinds of states are entangled versus which kinds of states are unentangled. So we can talk about a very special class of density matrices, product states, where we just take a bunch of row i's that are 2 by 2 density matrices and we tensor them together. And of course, the result that we get is itself a density matrix. But the important thing is that these types of density matrices that we get in this way shouldn't really be thought of as quantum objects at all because they don't have any entanglement. So one more twist on this definition is that maybe we won't just be interested in product states, but we'll be interested in mixtures therein. So I'll say that a state is separable if I can write it as a convex combination of product states, where I can write down some of these row i's, right? And the important thing is that, for our purposes, separable states are ones that only have classical correlations. So if I talk about measuring these density matrices, I'm not going to get anything that's inherently quantum about it, because I can realize these, instead as basically being like product distributions or mixture of product distributions. So let me say something trivial before we get to the main results. There's always something silly you can say about the relationship between the temperature and entanglement, right? Because you can always send beta to 0. Remember, beta is our inverse temperature. So what we're doing is we're just setting it to, we're setting the temperature to infinity. In that case, it's very obvious what happens to the entanglement. Because if I were literally to set beta equals 0, all I'm going to get is I'm going to get some scalar multiple of the identity. And this is something that is trivially separable. Because I know exactly how to write it as a product state. It already is written in exactly that form. So in some sense, we already know a very crude statement that if the temperature were infinite, obviously there's no entanglement in my quantum spin system. But the point I want to make is that this is a non-physical temperature. See, if you think about quantifiably how small you need beta to be or how large you need the temperature to be, the point is that as my system grows, the number of qubits I care about, I actually need the temperature to be growing too. In fact, I need beta here to be like 1 over 2 to the n to say anything non-trivial about this. So this is not like, it's not even like taking your spin system and throwing it into the sun. It's like doing something even worse to it, right? So a lot of times in classical spin systems, what you really care about are physically meaningful temperatures. What I care about are proving phase transitions about macroscopic phenomena where I can identify where the action is happening in a way that's scale invariant of the system. Maybe it only depends on things like the strength of the interaction and the degree. For each qubit, how many other qubits is it interacting with? So that'll be the name of the game here, is I still want to understand the relationship between temperature and entanglement, but I want to do it in physically reasonable settings, which this trivial version of what I'm saying is definitely not, right? So what happens at physically realizable temperatures? So let me tell you about our main results. So we showed was that what's called the sudden death of entanglement. So this was the first mathematical proof of it. So it turns out that if you have a quantum Gibbs state, remember that the terms in the Hamiltonian are tensor products of k Paulis. And we've normalized so that the coefficients we add them up with have absolute value at most 1. Then in that case, we define 2 different parameters, d and k. So d is the degree. So you care about, for each of the qubits, how many different terms in the Hamiltonian hit it, right? That's the degree of interactions. And then you care about k, which is for each of the terms in the Hamiltonian, how many different qubits does it touch? Then it turns out that if those are constants in your spin system, which usually they are, then there is some universal constant that, when the temperature is above that threshold, it's not just that the entanglement is very small, but that it's literally 0. There's not a shred of entanglement in this, right? So in some sense, this result was a little surprising to us. In fact, we proved the theorem without knowing we proved it, which is kind of an interesting quirk. The thing we were really interested in was an algorithm for preparing quantum Gibbs states. So what we wanted was an efficient algorithm that maybe sidestepped our inability to prove things about Lindbladians or Davies generators. And we wanted some other algorithm that can prepare quantum Gibbs states. And I'll tell you what that algorithm is. But somehow what was kind of a cute accident was that as a byproduct of showing that algorithm worked, we accidentally proved this theorem, about the death of entanglement. So somehow you get this very interesting physical phenomenon as a result of taking an algorithmic perspective on things. All right, so let me pontificate about some stuff. Maybe this will be controversial, I don't know. But I'll just say some things before I tell you about the proof. In fact, the proof is not too hard, so I can give you the main ideas of the proof just in whatever time remains for this talk. But I want to take a step back, at least as an outsider to quantum spin systems, and at least tell you some thoughts that are going around in my head. So if you think about quantum computation, certainly one of the main goals is to give quantum advantage, but for useful problems. So we all know about Shor's algorithm. So we know that if we had general purpose quantum computers, we could do things we believe are not solvable in polynomial time. We can break RSA, and the world would forever change. Of course, we don't have general purpose quantum computers yet. Maybe we will in some time. Probably doesn't seem like it's anytime soon. But one of the goals that people put up in the interim was quantum supremacy. And there it's a very different change on what you're aiming for, because what you want is any problem, no matter how artificial, that quantum computers that we currently have seem to solve, and classical computers seem not to be able to solve. So there are some caveats that come with that, which is that a lot of times you end up with problems that aren't so useful. They don't help you do interesting things, because you build some quantum device and it sort of computes whatever it does in nature. And then even worse, you sort of don't get much, there's no great ways to have a system of beliefs about whether there aren't better classical algorithms for doing it. There's been a lot of ebb and flow on what people believe. But certainly a lot of us here in this room believe that one path to useful quantum advantage is quantum Gibbs samplers, right? So we could hope that maybe quantum Gibbs states describe the natural world around us. Maybe they help us probe in the sciences to understand quantum phenomenon in chemistry or condensed matter physics. And we could hope that if we have even near-term quantum computers, that we discover new science as a byproduct of it, right? But the point I want to make, at least thinking about it from a complexity theory standpoint, is that there's a limit to how optimistic you can be about this. Let's say our goal was to do quantum advantage for some useful problem, for science, for quantum chemistry or condensed matter physics. And even in our most optimistic of days, the trouble is that there are some things we probably shouldn't expect to do with quantum computers, because we know even classically these things are computationally hard. So the thing is that even for classical spin systems, it's not just that there are phase transitions in things like magnetization, but there are phase transitions in everything you could imagine. There are phase transitions in temporal mixing. There are phase transitions in strong spatial mixing, like in Ewin's talk. There are even computational phase transitions, where the problem of sampling from the corresponding Gibbs distribution or approximating the partition function goes from computationally easy, solvable in polynomial time, to being NP hard. Yes?
Like, like for example, these cases is like a glass, but there the physical glass is not in a Gibbs state either. So
that's right.
Those would correspond to cases where like a Gibbs state is not really the...
That's right, that's right. So that's an even better topic, which I will get to later with even more controversial takes, but fantastic. So I'll get there, I'll get back to that. But my point is, if you believe that BQP does not contain NP, then all of a sudden we have these classic works of Alan Sly and Nike Sun that tell us some line in the sand that we must not cross, right? At some value of beta, when the temperature is low enough, we know that the problem becomes NP hard. In fact, even worse, if we think about k equals 2, so maybe we're just looking at spin systems which interact across edges, then the trouble is that we know that for beta above some constant C prime over D, where D is the dependency degree of the graph, the problem becomes NP hard. And now something kind of crazy has happened, which is that we were trying to give algorithms for preparing quantum Gibbs states, for high enough temperature, for low enough beta. And those algorithms worked, within a constant factor of the threshold where the problem becomes NP hard. But unfortunately, they also show that there's no quantum advantage to be had there, because there's literally zero entanglement. So all of a sudden, this dartboard that you're aiming for, it becomes very narrow in terms of where we could hope for there being a quantum advantage. And it's not obvious to me that there's anything here at all. That would suck. All right. So let me tell you about some independent work, which was really nice, of Rouget, Franca, and Alhambra. So in parallel, so they gave a polynomial mixing time bound for quantum Gibbs sampling, again at high enough temperature. Their work is really beautiful. I think probably many of you have read this paper too. So there's some differences in our bounds. So they get a better dependence on locality, so k versus k squared, but a worse dependence on the degrees. So we get D, which is optimal, according to this NP hardness threshold, whereas they get D to some constant, maybe it's 6 or 12, something like this. In fact, these were the folks that were so kind enough to point out to us that our theorem about preparing Gibbs states accidentally proves this result about no entanglement. So we're very grateful to them for telling us what our theorem said. Okay, so now what I'm going to do is I'm going to roll up my sleeves and we're going to do the proof. The proof is not that hard, but it's strange. And I think the only way I know how to explain this proof is by explaining a metaphor with classical spin systems, because maybe that's where it came from in some ways. So first, let me tell you about some elementary tools to get us over the hump of starting to think about separability. So we already talked about this idea that you send beta to literally 0 and you get out a multiple of the identity matrix for your Gibbs state, and it's obviously separable. Now the hope is that if beta is merely very close to 0, then what you're getting out is not the identity, but is a perturbation of the identity. And you could hope that perturbations of the identity, if the perturbation is small enough, preserve separability. Now, some version of that is true. It's just that quantifiably, it's very weak. So here's the fact, which is not hard to prove in a very direct sense. And sort of the point is that I over 2 to the n is not just separable, but it's strictly inside the set of separable states. So somehow there's a quantified amount that you can move it by and still maintain the fact that you can write it as a mixture of product states. But when you work out how far you can move it, well, I take the identity and I perturb it by some traceless matrix with operator norm at most 1, and maybe I've got a constant c, that's my tuning parameter in front. The point is that when c itself is incredibly tiny, 1 over 2 to the n, then it's easy to show that rho is separable. Now this is completely useless for us in this form, right? Because this is what I was saying, was that you take your system and you throw it into something hotter than the sun. It's got inverse temperature 1 over 2 to the n, and that gives you a small enough perturbation of the identity that everything is fine. And this is not what we wanted, because we don't want n's in here. Now, it might look completely useless, right? But there's a slight twist on this fact that puts us in business. And it's actually just a trivial corollary of this fact. See, the point is that if instead I tell you a bit more? What if it's not just a traceless perturbation of the identity, but moreover I tell you that E has support at most k? So it looks like some matrix that's 2 to the k by 2 to the k tensored with the identity. What I claim is that I can straightforwardly replace this bound on C. Instead of it being at most 1 over 2 to the n, it's at most 1 over 2 to the k. And the proof is dead trivial for this, because you're just tensoring with the identity, so n becomes k. So the entire point of this is that locality helps, right? When we look at perturbations of the identity that maintain separability, when those perturbations are local, we're in business. But that's not all there is, otherwise this would be a very short talk, and I'd have a lot of time for controversial statements at the end. But the problem is the matrix exponential. That's our foe that we have to fight with, right? H is local because it's literally the sum of local things. But e to the minus beta h, is that local? Is it quasi-local? What does it look like? That's the entire name of the game, is understanding how locality of interactions manifest into locality, in the macroscopic object. That's what the name of the game is in classical and in quantum spin systems. And what we're going to need are carefully designed expansions that you would never think to write down unless you were thinking about it, I think, in the classical way through something called disagreement percolation that I'm going to tell you about. So let's take a detour. Let me tell you some more about classical spin systems, just as a backdrop to what exactly these expansions are and where they come from. So we talked about classical spin systems. We know what Ising models are. They're a very concise language for describing high-dimensional distributions on plus minus 1 to the n. And I told you that there are some computational phase transitions. When beta is too large, the problem becomes NP hard. But amazingly, when beta is any smaller than that, for a lot of models, we know bounds on, algorithmic bounds on the running time and, of sampling from an Ising model. So how exactly do you sample from a Gibbs state? There's a very natural Markov chain that's called the Glauber dynamics. And it operates with a very simple principle. You start with an arbitrary state. So maybe I've got black dots that represent spins going in one direction. I've got red dots that represent spins going in another direction. Now, obviously, the state is arbitrary, so it has nothing to do with the Gibbs distribution. But what do I do? So what are the steps of my Markov chain? Well, what I do is I choose a node at random, and then I erase its state. And now there are two choices, for how to fill in that missing spin, right? Because I could color it in red, or I could color it in black. Now, in general, it's either computationally hard or mathematically hard to get a handle on the partition function. So I don't necessarily know what is the absolute probability of this configuration of my Gibbs distribution that I want to sample from. I don't know what is the absolute probability of this either, all because I don't know Z. But the important thing is here, all I need to know is the ratio of their two probabilities, because that's the thing that governs the probability I should take one branch versus the other. And the important thing is that now when I look at the ratio of their probabilities, that doesn't depend on Z at all. In fact, it doesn't depend on most of the spin system. All that matters is what's happening around the site, right? Because it matters whether he prefers to be the same or different than his neighbors and by how much. So without a lot of math, that's how Glauber dynamics works. You start with an arbitrary state. Every time step, you erase a site at random, and then you re-randomize it with the conditional distribution on how you should fill in the missing spin based on the way that I've defined the Gibbs distribution, right? And the way that you define this, there are a lot of natural properties that are just very easy to show. You can show that there's a unique steady state distribution that really is the Gibbs distribution that we would like to sample from. Then the name of the game is really just, when does this work? I've got a Markov chain that's on 2 to the n things because it's cycling over all possible states in my system. And the question is, when does it have rapid mixing so that its mixing is polynomial in n, versus when does it have torpid mixing where the mixing time is exponential in n? And now I can tell you about a very powerful lens for thinking about when you get mixing time balance for classical spin systems. And this is kind of a crude tool, because it doesn't give you the sharpest bounds, but somehow it's the most flexible tool. So you don't even see it that much necessarily, but let's do it as a thought experiment. So imagine I'm trying to sample from a very high temperature Ising model, right? And I could imagine that my Glauber dynamics re-randomizes this spin, xi, and then maybe the next site it updates is xj, right? Now, if we think about it in the high temperature case, the point I want to make is that if you're really in high temperature, not 2 to the n temperature, but some constant, then you should really think about this spin as being almost equally likely to be red or black. Maybe the marginal probability that I fill it in one way versus the other is somewhere in the range 0.49 to 0.51. So it's somewhat close to a coin flip, but it's not exactly 50-50. So the way to think about it is, in principle, my Glauber dynamics, the way that it chooses the spin, is it has to look at the conditional distribution that it should be, which depends on its neighbors. But sometimes when I throw that dart, I land outside the ambiguity region, that region between 0.49 and 0.51. And then I don't actually care what my neighbors are. I can already decide whether my spin should be up or down, just because it's close enough to 50-50. So that's the way to think about it, is that there's something you can do called disagreement percolation, where the idea is that at high temperature, this guy looks almost like he's independent of everyone else. He's not quite. I throw a dart in the hopes that I land outside the ambiguity region. If I do, then I already know his spin and I can move on from him. But if instead it lands in the ambiguity region, I have to phone a friend, because I don't know what my marginal probability should be. It depends on what my neighbors are. So in that case, maybe if xi's dart lands in the ambiguity region, I then have to do the same process for xj. Maybe I get lucky here and I can decide on his spin and return and figure out the spin of xi, or maybe the process grows. But the entire point is that this acts like a percolation. So when you think about the corrections to the fact that it's not a product distribution, which you should think of as being a separable state, then most of the time I'm going to get lucky, and I actually can decide on some spin. But when I don't get lucky, I have some chance of opening an edge to the neighbors. But then the process is likely to die out there. Okay, it might move on and become even bigger, but the whole process is subcritical, so you're very likely for the thing to die out. And that's the intuition, right? Is that you end up with these small connected components, and this is where locality comes from, right? We would hope that there's some manifestation of this for spin systems, and that this is what allows us to prove these kinds of death of entanglement things. So now let's roll up our sleeves for real, and let's do the quantum case, right? So inspired by this classical idea of disagreement percolation, here's the strategy. I don't want to prove no entanglement in one shot. I don't want to prove separability in one shot, but I'm going to prove it one piece at a time. So I can say that a Gibbs state is one versus all separable. If I can write it as a convex combination of product states, but if I can write them instead as a tensor product of rho 1, where that's a 2 by 2 density matrix, tensored with something else that's 2 to the n minus 1 by 2 to the n minus 1. So in this case, I'd be happy because somehow I've cut the entanglement from the first site to the rest of my system. And the whole hope is that we can proceed by induction. If we can start off with our Gibbs state and pull out the first site and say that it's one versus all separated, and then we work with the remaining system on n minus 1 qubits and pull out the next qubit and say that it's one versus the rest separated, then we can hope that we can induct and prove the bound that we want. So the key is how exactly we're going to show this one versus all separation. And that's going to take me to something called the extraction operator. And this is the main mathematical object that we introduced to make this work, right? So what I can do is I can take my Hamiltonian, which remember has these terms HE, which are edges. They describe which sets of qubits interact with each other. What if I just separate out all of the terms that involve the first site, right? Those are the things I want to get rid of and treat separately, because those are the things that connect the qubit to the rest of the system. So now I can define what the extraction operator is. So it looks, e to the minus beta h over 2. You'll see why the 2 is there later. But then what I'm doing is I'm also multiplying by an e to the positive beta of h minus h1 over 2. So let's forget about the 2's. The important thing is that when I take h minus h1, that's a new Hamiltonian, but now nothing is acting on the first site. So you should think about this extraction operator as some way, analytically, to go from the Gibbs state I started with to some other state which has a simpler Hamiltonian so that I can induct. And the entire name of the game is, what does this extraction operator look like? What are ways to do the right cluster expansions so that we can control it? Okay? So let me tell you the key lemma, and then I'll give you some intuition for it. So I defined what M1 is, this extraction operator. And the point is that you can write it in a series expansion where you've got coefficients that are decaying for small beta because they're getting smaller and smaller exponentially. But then you've got these matrix words like polynomials in H and H1. And these FKs are going to have some way that you can write them as a linear combination of Pauli operators, tensors of Pauli's. But the important thing is that these coefficients are small. So what you want is the property that each of these AIs are normalized. So their operator norm is 1 because they're tensors of Pauli's. They're supported on connected components of size at most k plus 1. And that you can bound the total mass of all of the coefficients. So if you've seen cluster expansions, this is the same basic principle at play. As somehow I want some sort of expansion of this extraction operator that doesn't tell me it's literally local, but it tells me it's quasi-local because the amount that it has this degree k term is attenuating, at least at high temperature, right? So that's the name of the game, is to prove this kind of lemma. And the point is very simple now, right? Which is if your coefficients grow like d to the k, then as long as your beta is small, like 1 over d, then you're in business because you can actually say that the part of your extraction operator which is happening, that acts on a lot of sites, is also comparably small. So think back to that fact prime I gave you. As long as you're looking at less and less local perturbations, as long as they're smaller and smaller in norm, you're good and you can maintain separability. And that's all that's happening here term by term, right? So the entire name of the game is, how do you prove this kind of lemma? And if you had this kind of lemma, the rest of the proof is very easy, just to finish what's going on. So we can take M1 dagger, right? And the important point is that the way that I defined M1, it literally gives me what I want, is that it's a way to write the Gibbs state, forget the normalization of Z, as some sort of relationship to this new Gibbs state where I've changed the Hamiltonian to remove all the terms that involve site 1. But now M1 is somehow the correction term. So if M1 has this series decay where the terms that are larger and larger are attenuating exponentially, then so does M1 dagger. And this entire thing is separable, right? And then the point is that if this is separable, if I think about what this is doing, it's literally not acting on the first site. So it maintains the fact that it's 1 versus all separated. So if we had this key lemma, we would be done, because it would literally tell us we're acting on the separable state by something that preserves some modicum of separability in our system, right? And so you can push this through. Induction is a bit complicated because, the thing I'm inducting on, it doesn't literally get me back to the identity, but, let's just sweep that under the rug. Let me tell you the last part of the story, which is, why exactly does this extraction operator have this benevolent series expansion? And so, what do? Well, you can just, compute the power series, the matrix power series for these exponentials, and you get exactly this expression right here, right? This is coming from the e to the h minus h1, and this is coming from the e to the minus h. And now the important thing is what I can do is I can collect terms. Like, what if I collect all the terms so that the total power is k? Because I'm looking for the degree k part of my expansion. Then what's going on is I'm going to pick up these binomial coefficients of like k choose j, because I have a certain number of ways of choosing them out of here and choosing them out of here and correcting them. But this rearrangement just gives you an expression for M1, right? And this is a very simple combinatorial identity, and that's what our FK is. So I promised you that M1 has this exponential decay, and you can write it in terms of these FKs that grow onto larger and larger supports, right? And now the remaining part is just to interpret what these FKs are. See, I need to say something that they're not too large, otherwise all hope is lost. And now the really fun part comes in, which is I claim that these FKs actually satisfy a very nice recurrence, that you can express FK in terms of FK minus 1s. So in fact, the way to think about this is that if you ignore the non-commutativity, this is like the kind of binomial identity that you ask undergrads to prove in discrete math, because it's all about some sort of binomial expansion. And you're just figuring out whether you choose k minus 1 from one part versus k minus 1 from another. All that you have to do is you just have to make sure that you multiply on the correct side by either h minus h1 or h on the right, right? Because all the h's are happening on the right and all the h minus h1s are happening on the left. So this identity, you can just verify it for yourself, but you should really think of it as a non-commutative identity of something that's really not so exotic. And now you can write this identity, this recurrence for where the FKs come from, and you can write it as a recurrence involving the commutators. So I can collect the terms that involve h, I can collect the term that involves h1, and all that's happening is, the recurrence is telling me how exactly FK grows. And the important thing is that, for the commutator, if I take any two matrices A and B, well, if their supports are disjoint, the qubits that they're acting on, then their commutator is going to be 0. But otherwise, if their supports are not disjoint, then whatever I get out of the commutator is supported on the unions of their supports. So when we have this recurrence where I'm defining what FK is in terms of commutators with h and FK minus 1, then I can expand what h is because it's just the sum over a bunch of edges, and the commutator is linear. And this means that FK minus 1 is just growing along these edges. And that's where these connected components come from. It really is the same kind of percolation process that I told you about in the classical case. It's growing out connected components. But every time we do that, we pick up extra factors of beta because we're close to the identity, or we're close to being 50-50 for our distribution, so that we have this subcritical process that's growing. And that's exactly where it comes from, is that you can visualize how these supports grow, and they grow in a very nice combinatorial way based on the edges of your graph. And that's really the essence of the proof, is that you have this extraction operator that shows you one versus all separation so that you can prove by induction. And the way that you prove that is really just based on this series expansion and realizing it in terms of a generating function. So I promised for the last couple minutes, I guess I would say some controversial things. So let me tell you about some of my favorite questions here. See, in classical spin systems, we have not just an understanding of phase transitions, but we have a relatively sharp understanding of phase transitions. For a lot of different spin systems, we can pin down an actual beta and say that this is the beta where the system dramatically changes. Now, a lot of properties in classical spin systems, they change together. Things like where there are zeros in the complex plane of the log partition function. Things like where you have strong spatial mixing, where you have rapid mixing for Glauber dynamics, where you have computational phase transitions. They all have the same beta. But does entanglement have a sharp phase transition too? Does it happen at the same threshold as these other computational phase transitions? This seems like an amazing question. In fact, I don't even know how to make predictions about that, because there are a lot of heuristics in statistical physics for making these kinds of predictions in classical spin systems, but I don't even have a system of beliefs about how to approach this kind of question. And critically, does this transition happen earlier than NP hardness? You can also ask the same way that we have a fairly cohesive picture in the classical setting of how dynamical properties imply structural properties about Gibbs states. Can you do that for things like conditional mutual information? Ewin gave a talk this morning exactly about this. But there's still more questions than answers there, especially about recovering the full version of these KKB-style papers. And I think my meta question I find most exciting is, I'm an interloper here in this quantum workshop. I don't really know much quantum. It's fun learning from you guys. But I have this vague sense that a lot of the things I hear, these buzzwords, there is this sort of dictionary connecting it to the same type of language and ideas in classical spin systems. Some things change, like the Markov property fails, but maybe there's a bit more of a dictionary between these areas than we give ourselves credit for. That would be really exciting. I think there are a lot of other interesting questions about whether metastable states are sort of better ways to try to understand predictions of materials. That would be my own personal belief, is that somehow maybe looking at Gibbs states in the first place has this danger that it's not that connected to the physics we want to predict. Maybe even better, in areas like mathematical physics, they use a lot of symmetry and translation and variance, not just bounded degree and bounded locality. And you can have very different phase transitions that happen, and use a lot more tools from areas like representation theory to pin them down. So when you talk about very well-behaved systems like, Fermi-Hubbard types of models, maybe there's more of a dictionary one has to build with mathematical physics. So I'll end there. I have more questions than answers, but I'm happy to take any questions you guys have. Otherwise, thanks for the attention.